got you. Sorry.
This call is now being recorded.
So last class we spoke about the timeline of quantum physics or chemistry, whatever you want to call it. And we noticed that there were discoveries, experimental discoveries, which could not be explained by classical mechanics. And then people came up with some smart ideas to figure out what the problem was with the classical theories, and this led to quantum mechanics. So we'll go into a few examples of these failures of classical mechanics and how they were solved. And we'll go more or less historically. So the first observation that we encountered a problem with was black body radiation. So it was recorded in it was recorded really, really long ago. I've forgotten the date now, so let's just go back. So, yes. So Kirchhoff recorded the black body spectrum in 1860. So, and then 40 years later, in 1900, Planck explained it. So let's see what he recorded. So the black body radiation plot that he obtained. Okay, what is a black body? Okay, so this is something, of course, we've done in +2, in class 11 or 12. So a black body is something that can emit radiation of all frequencies. It can also absorb radiation of all frequencies. So it's sort of an ideal body. And you can experimentally realize it by having a sort of a ball or object with a little hole in it and covered in carbon black inside. So if you have a hollow cavity with carbon black, you can realize a black body experimentally in the lab. The most natural black body and the easiest one is the sun. It emits light of all frequencies. However, you cannot really experiment with sunlight because it is not controllable to that extent, and there is scattering and there are other issues with it. So Kirchhoff designed a black body, like I said, like a hollow cavity lined with carbon black, and he recorded the spectrum. So by recording the spectrum, what do I mean? He plotted the intensity of emitted light versus the frequency of the light emitted on heating this black body. So you're basically heating something and it is glowing and emitting some light, and you're measuring the intensity of each frequency of light that is emitted. Okay, and what he found was that the experimental plot looked like this. So this is labeled as quantum in the figure, but this is also what the experimental plot looked like. Now, according to the classical law, okay, or the classical theory of radiation, you would obtain a plot that looks like this, like what is labeled as classical. Okay, and you can see that it is totally unphysical. So what the classical law tells you is that as soon as you heat this black body, you will have a huge amount of energy emitted at high frequency and very little at low frequency. So this is what it tells you. So, but this is very strange, right? This is not what happens. You can see that if you have heated something to a certain temperature and it is emitting some light, then it's not all UV or X-ray or something. There is a peak somewhere in the middle. And if it's in the visible region, it is basically the color at which this object is glowing. So this was totally unphysical, what you got from the classical theory. And the fact that the theory gave an unphysical amount of, or predicted an unphysical amount of energy emitted in the UV and beyond range, this was called the ultraviolet catastrophe, which meant that the theory was fine when you were dealing with very low frequencies of light, but as soon as you tried to predict the intensities for higher frequencies, you got unphysical amounts. Okay. Then Planck explained it with his quantization proposal, and he got a plot which followed exactly the experimental plot. So we will do details of this derivation as well. In addition, the other experimental observation was by Wien's law. So what was Wien's law? Wien's law was that if you recorded this black body spectrum for different temperatures, okay, then you could notice that the maxima of these plots shifted according to the temperature. So when you had low temperatures, you had a peak at a larger wavelength. So notice that this is now wavelength. And when you have high temperatures, the peak is at lower wavelengths or higher frequencies. And when you join these peaks, you get a plot that obeys lambda t equal to some constant. And this and he calculated this constant to be 2.898 into 10 to the power minus 3 meter Kelvin. So this was an empirical law. So this is not a law that is derived. It is obtained by fitting experimental data. Okay. So this was Wien's law. So of course, whatever theoretical model you put forward for black body radiation, it has to also give you Wien's law theoretically. Okay. Then let's just see in mathematical terms what it was. So the classical theory of black body radiation was put forward by Rayleigh-Jeans, and he said that the spectral energy density is given by 8 pi nu square by c cubed kt. So this is obtained from the classical law of equipartition of energy. We will do the derivation of this, okay? And then you can see from this, so what is spectral energy density, by the way? Spectral energy density is the amount of energy that is emitted between nu and nu plus d nu, nu being the frequency of light. So in a very small range, infinitesimally small range, what is the amount of energy that is emitted? Okay, and this was called Rayleigh-Jeans law, and it suffered from the ultraviolet catastrophe. Obviously, because the energy is directly proportional to nu squared, which means higher nu, higher energy.
Ma'am?
Yeah?
Ma'am, can you please explain this graph once more?
Sure. So the graph is basically, so these are the two theoretical plots. So if you use the classical law of equipartition of energy, then you get an expression for the energy density. So the energy emitted in the frequency range nu to nu plus d nu. It is 8 pi nu square kt by c cube. So then so what you get is basically, with increasing nu, you have more energy. So that is this plot, this classical plot. Okay. Then, but this is unphysical, like I said. The experimental plot looks more like this, like the one you get from quantum theory. So I can say maybe that this is quantum and experimental.
Ma'am, we can see from the expressions that how it will result in interval catastrophe and how it was solved by the Planck's law. But can you explain, I mean, what theoretical reason was given that limiting certain frequencies, certain energies of photons will resolve this? I mean, how? Because there
Yeah,
are
we will
low
do the
energy
derivation.
photons, no?
We will just do in like 1 minute, we will start the derivation and you will see. So we will do the derivation of both Rayleigh-Jeans law using the classical equipartition theorem. We will also do the derivation of Planck's law where the quantization is introduced. So you will see how it follows. Okay. So now I just want to tell you why the plots look different. So here you just have nu square, and when Planck introduced the quantization, you ended up with an additional factor over here, which modulated the high frequency part, and you got close to the experiment. So now we will go to the derivation. Okay, and hopefully everything will become clear.
Ma'am,
Yeah.
can you explain, define the term spectral and spectral energy density once more?
Sure. Spectral energy density is the amount of energy emitted in the frequency range nu to nu plus d nu. So nu to nu plus d nu. So let's do the derivation, then I think everything becomes more clear. So I will upload a PDF called blackbody radiation.pdf, which will have the classical derivation. So you can look at that document.
Excuse me, ma'am.
Yeah.
Ma'am, is the spectral energy density, which that mu, is that the energy emitted per unit time, or in the frequency? Is it?
No, time is it is not. Time does not feature here. I mean, this is just not per unit time.
Ma'am, if I'm right, then the spectral energy density is the height in the graph, right? For each frequency.
Yes.
Okay.
It is the y-axis basically. So this is u. So I refrain from writing u directly because intensity and spectral energy density have some unit differences. So they are related but not quite the same. So, but if you plotted u versus frequency, you would get a similar looking plot as well. But in experiments, you measure intensity. So u multiplied by some constants is basically intensity. But then I am not going into those details because you'll see physicists have some little bit of a different definition and chemists have a little bit different, and it also changed over time. So I don't want to go into the complication. For your purpose, spectral energy density and intensity are equivalent. They're not exactly the same, but they're equivalent. Okay, so let's see. So I just, in the slide, I've just listed what you must know, what you have to learn. So one is you have to know how to derive the spectral energy density for black body radiation from the classical equipartition theorem. So the classical derivation of Rayleigh-Jean's law. And then you have to know how, when you quantize it, how you get Planck's law. Okay. And then from Planck's law, you can go back, like in some limits, to Rayleigh-Jean's law. You can reproduce Wien's law, like I said, and you can also reproduce Stefan-Boltzmann law, which is basically the law which governs the energy released with temperature. So sigma T to the power 4, if you remember from your +2. So this is what you will have to know. I will, of course, go through each of them. Okay. So let's start with the classical derivation. So I will. This is, what is it called? It's called Quantum Chemistry 1. Quantum Chemistry 1. I don't like the one with the dots. Okay. So this is black body radiation. So everyone can see my screen?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So black body radiation. Let's see. So, like I said, a black body is basically a cavity with a little hole through which the radiation comes out. Okay, and inside this you have the radiation being generated. So you have standing waves being created by reflection of these of this light inside, and then this light comes out and you collect them on with some sort of instrument. Okay, so detector. So this is what it looks like. Now, for the purpose of derivation, we consider a large cubical cavity. So let's say I'm just drawing one side of like one direction of the cube. Okay, so this is of length A. So it's a cubic box of length A, and we are measuring a certain range of wavelengths, and the maximum wavelength, so that is measured. So what should I say? Maybe if I write lambda max, okay, let's just say lambda. And lambda is very much smaller than A. Now this is very easy to achieve. Any normal sized cavity is much larger compared to the wavelengths of light. Okay, so lambda is the longest wavelength measured. Fine. Now, in this cavity, you have standing waves being created. So let me put it in a different color. So this is one mode, so the lowest mode. Then you have this. Then you have, okay, different color again. So maybe something like this. So these are like various modes of standing waves that you can generate in this cubic box.
Ma'am,
Yeah.
when you say standing waves, of what are you saying? I mean, standing waves of what
Of
exactly?
emitted light. So I am heating this black body. So there is heat. When I heat it, so this is a hollow cavity. So the light is generated inside. Okay, and then inside there are multiple reflections, and only the standing at thermal equilibrium, only the standing waves survive, because if you have some sort of amplitude at the walls, they will generate currents in the wall and they will get absorbed. So eventually when you reach equilibrium, you will only have the standing waves available inside the box, and it is only these standing waves which can then come out of this little hole over here. So that is the concept that we are using here. Okay, and the amplitudes are, of course, this is light, so you can say this is the electric field or the magnetic field, however you like to represent light. Okay, yeah.
Sorry, I didn't understand what you explained. Could you
Oh,
explain?
yeah, sure. I'll explain again. So you see, the walls are generating this light, okay, and they're generating the light in all sorts of phases. So some wavelengths, let's say. So if I have a wavelength which goes like this, okay, if one of the light waves, then what will happen is the walls will absorb this radiation because it will generate currents in the wall. So eventually when you reach thermal equilibrium, this which means that now the object is at a steady temperature. So as long as they are absorbing light, the walls, they are not in thermal equilibrium. So the temperature will change for this object. Then when all this half waves or whatever things which look like this, they get absorbed, then the only light that can remain inside are the standing waves, because they have zero amplitude at the walls, so they don't get absorbed.
Okay, got it.
And this surviving radiation, this will come out of this little hole, and I will only detect this radiation. So that is the idea.
Okay, good. Thank you.
Yeah.
Ma'am,
Yeah.
for that we have to consider that the hole through which it is coming out, that is very smaller than the amplitude.
Yes, yes. This is a very small hole.
Okay.
So, ma'am, the only standing waves that will be left, like so A will have to be a kind of like a whole number multiple of the wavelength or something.
Exactly. So we are just
Okay,
going to
okay.
do that. So that will be very important for us to count the waves. Okay. So the standing waves correspond to integer multiples of lambda by 2. So n lambda x by 2 is equal to A, where n is equal to 1, 2, 3, whatever, some integer. Okay. Then now we're going to so similarly, you can say this is the same. So I have only drawn it for the x, but of course it's the same for y. So I can write nx. So now I'm labeling the n with x. Or I can put an x here as well. So nx lambda x by 2 is equal to ny lambda y by 2 is equal to nz lambda z by 2 is equal to a. It's a cubic box, so everything is a. Okay. So now, so here, so what have we implicitly done? So here we've only considered waves which are either parallel to x-axis, parallel to y-axis, or parallel to z-axis, right? So this means that only light whose let's say direction is parallel to sides of the box have been considered. Okay, but if we have an arbitrary wave in the cube, so in some direction, which makes some angles with the x, y, and z axis of the cubic box, then what is the condition? So to do that, let's draw a little bit of a more complicated diagram. So I have a, I'm sorry, it's difficult to draw straight lines on this. So, okay, x and y. And then I have, this is A. Okay. And I have a wave which is moving in this direction, let's say. Something like this. Then it makes an angle alpha with the x-axis and an angle beta with the y-axis. Okay. And this is, so this length is lambda. Okay. Fine.
Ma'am, you are not audible.
Yeah.
Uh, for past 1 minute, you are not audible. 1 minute, you are not audible.
Oh, I was not audible. Oh, I'm sorry. Okay. So I'll draw this. So I have drawn a cubic box, and let's say this is now the. So this arrow here, this is the direction of propagation or direction of the wave normal, you can say. Okay, and then you
Ma'am?
have some.
Ma'am, where exactly is black body in the figure?
It's this cube, so it's one slice of the black body, the x and y.
Okay. Okay.
And the lambda is traveling in this direction, and this wavelength is so I've drawn some wave fronts. If you remember, the dotted lines are the wave fronts, and this is the lambda wavelength. Okay, and I am calling this as I'm calling the projection of the gap between the wave fronts. I'm calling this as lambda x. Okay, makes sense. So I'm not projecting lambda on this. So this is not what I am doing. Okay, I'm calling this as lambda x. Okay, and then I'm considering this triangle, this right angle triangle. Then I can say that lambda x cos alpha is equal to lambda. So be careful. So I'm not projecting lambda on the x-axis or lambda on the y-axis. I am saying that the intersection of the wave fronts on the x-axis, those are separated by a distance lambda x. Okay, then lambda x cos alpha is lambda. Similarly, so I can say lambda x is equal to lambda by cos alpha. Then similarly, lambda y is equal to lambda by cos beta. So this is what I have done in the figure, and I can extend this to 3D and say that lambda z is also lambda by cos gamma, let's say. Okay, now we know the sort of standing wave condition for lambda x, lambda y, and lambda z, which is that which is what
Ma'am,
yeah.
excuse me. But why we are taking I mean the projection such a manner? We could have take I mean where it's actually lambda into cos alpha, that kind of projections. I mean that's my question.
Because we know what the standing wave condition for the wave fronts along the axis are. So this helps me use that. If I projected lambda on the x-axis, it doesn't really help me. So it's just this is what works out basically, because what
Ma'am, the dotted lines in blacks are wave fronts.
These are wave fronts, yes.
And the distance between them is lambda.
The distance between them is lambda, yes.
Okay. Now I understood. I somehow misunderstood. Okay, thank you.
Okay, so then lambda z is lambda by cos gamma, and then I can I'll go back to black. So then we had that nx. So from what we had before, nx is equal to 2a by lambda x, right? So that is equal to 2a now by lambda and then cos alpha. Similarly, ny is equal to 2a by lambda y. This is nothing. That is equal to 2a cos beta by lambda, and nz is equal to 2a by lambda z, which is 2a cos gamma by lambda. Okay, fine. Now I square and sum them. So nx squared plus ny squared plus nz squared. This is equal to then 2a by lambda square. And you have cos square alpha plus cos square beta plus cos square gamma.
And that will be 1, right?
Yes, so this will be 1. So then I get 2a by lambda square. Okay, and then from here I can get the allowed frequency. So now I make lambda the subject of the formula. So lambda squared is equal to 2a.
Ma'am, could you explain how the square of the cosine terms is 1?
This is a trigonometric identity. If you, let me see. So if you've done 3D coordinate geometry, then this is one of the important theorems.
Okay, I must have forgotten then. Sorry.
Yeah, I don't think I have also forgotten. I cannot do it offhand at the moment.
Ma'am, I have a question. The
Yeah.
nx are not somehow are by no means related to refractive index. I am right? Am I right?
No, they are not related to refractive
Okay.
index. They are just integers. They are just integers which tell you which standing wave I'm talking about. It tells you the mode of the standing wave. So lambda, okay, so let's get back here. So lambda squared is equal to then 2a squared by nx squared plus ny squared plus nz squared. And I can also write this as frequency. So lambda is c by nu. So nu square is equal to c squared by lambda squared. And nu is, okay, now I'll write it like this one. So nu is equal to c by 2a square root of nx squared plus ny squared plus nz squared. So this tells you basically so these are the permitted frequency modes. Okay. So now what do I need to do? So I have obtained an expression for the allowed frequencies. So for various triplets of the number nx, ny, nz, where all three are integers, I get various allowed standing wave modes. Now what do I need to do? Remember, I need to find out the energy between nu and nu plus d nu. So I need to count the number of modes. So how will I do this? Okay. So how it is done, this is also an interesting thing, is basically you represent each triplet of numbers as a lattice point in 3D space. So I am plotting all the allowed modes, each of them as a point in space. So what are my axes? My axes look like this. So again, I'm doing it in 2D, but you can, and then we will extend to 3D. So I have nx and ny. These are just integers. Okay. And I plot each allowed couplet. So how do I determine the allowed couplets? So given a frequency, I know what square root of nx squared plus ny squared plus nz squared will be. Right? So I have a value. So I determine all the allowed ones. So basically you will have more or less all possible nx, ny, nz. So I have some lattice points here as well. Okay. And now I consider a vector which I'm calling a rho, which is it's an arbitrary one. So let's say it goes up to here, and I draw a circle. Let's see if I can manage that. Okay, yeah, this one, and then I have another one.
Ma'am,
Yeah.
nx and ny are only defined at integer, I mean natural numbers only, right? But how can you take a vector to a random point which is not an integer? I mean, which is not a natural.
So what I will assume is that I have so many lattice points that I can do this. So this is something I will assume, which means I'm assuming a large number of modes, that is a very large cavity, such that a continuous distribution of n can be considered. So the condition basically is that the length A is very much larger than 1, such that in spite of the discrete distribution of points, I can consider a continuous distribution. That is an assumption that we will make.
Ma'am?
Yeah?
Ma'am, what you have drawn over the lattice points?
Over the lattice points, I have drawn an arbitrary vector, just like two. So this is 1/8 of a sphere or 1/4 of a circle in 2D. So this is so this is just a circular arc of length rho.
Okay, ma'am. Thank you.
You'll see why we are doing this. So this is just a very smart way of counting allowed modes between nu and nu plus d nu. So whenever we're talking about writing a function of nu, it means it will have to be a continuous distribution. But we saw that they are actually discrete. So at some point we have to so we have just realized what assumption we're making. The assumption we're making is that the box is so large that there are so many possible standing modes that you can consider a continuous distribution of nx, ny, and nz. Okay. And to do that, we're going to count the number of modes in the spherical shell between rho and rho plus d rho. So that is what we are going to do. Okay, so when I have two shells, one at rho and one at rho plus d rho, I can say that rho square is equal to nx square plus ny square plus nz square for that shell. Okay, and nu is then from this previous relation over here. So if I write this as rho square, then I can say that nu is equal to C rho by 2a. Okay. Now I'm going to count the number of modes having frequencies in the range nu to nu plus d nu, which is equivalent or which is equal to basically the volume of the or related to, I shouldn't say equal to, volume of the spherical shell between rho and rho plus d rho. Okay. So in 3D, okay, this shell, spherical shell is 1/8 of the sphere. I guess that is clear to you. So if it's in 3D, okay, so number of modes I am writing as n nu. Okay, and n nu in the range nu to d nu, that is n nu d nu. So at a frequency nu, the number of modes are n, and you multiply it by d nu, and or per unit frequency it's n nu, and you multiply it by d nu to get the number of modes in nu to nu plus d nu. So n nu d nu is equal to then 4 pi rho square, that is this shell, into d rho. Okay, and if it's 3D, then it's 1/8 of the total sphere. Fine.
So all the negative integers not we are not counting. That's what you're saying.
No, we're not counting negative integers. No. So that's why we're just drawing like one quadrant and then counting everything. So these cannot be negative. Nx, ny, and nz are all positive. We're drawing it just to make it easy to count. So this is 1/8 of sphere. That is where it's coming from. And we will also multiply it by 2. This is a different logic. This is because this is light has 2 possible polarizations for every standing wave. Okay. So what does that mean? It means that for radiation traveling in the x direction, for example, the electric field vector E can either be oscillating in the y direction or in the z direction. So that is what is meant by 2 possible polarizations for every standing wave. Oh,
Ma'am,
yeah.
excuse me, why are there only 2 possible polarizations? I mean, that is something I cannot understand.
So those are, you can that is say if you're saying linearly polarized light or something. I mean, the 2 are unique. It can so there are 2 independent polarizations. You can say that the electric field can be in anywhere in the perpendicular plane, of course. But if you want to count unique waves, then only 2 are possible.
Okay, so it essentially means that any light with any polarization can be made from combination of these polarizations.
Yes, that is why you can always split light into linearly polarized forms like plus and minus, or you can have clockwise or anti-clockwise circular polarization. So it's always 2 for every direction of light, 2 possible polarizations. And it's up to you whether you want to consider linearly polarized or circularly polarized. You've heard of this, right? Linearly polarized light and circularly polarized light.
Ma'am, that hasn't been taken actually yet. So.
Okay. But even in +2, like when you studied polarization, so you saw that you could either have like a clockwise light or an anti-clockwise light. So there also it's 2, and when it's linearly polarized also it's 2 for every direction. Anyway, so this is the counting part. So this is what you count, okay, and then you can replace this rho square d rho in terms of what we know. So this will be n nu d nu is equal to pi 2a nu by c whole square 2a by c d nu. Okay. And then so this is
Ma'am,
it. Yeah.
on the right hand side, there is 4 pi rho square d rho by 8. That will be the volume of that section
Yeah.
times 2 for each of the possible polarization. But what we have to number of, I mean, the number density of the modes, like how many modes there are in a unit volume, like that.
This
This is
is
just
so
a volume, right?
n nu is the is for like per unit frequency, and d nu is the range. Uh, this is what you mean? No.
No, on the right hand side, ma'am.
On the right hand side, so this is like, no, this is not a density. This is just the total number of possible modes in that shell. Like just the positive 1/8 of the sphere. No, maybe I'm not getting your question. Can you just repeat it?
No, ma'am. We wanted to count how many number of modes there are between nu to nu plus d nu, right?
Yes, and we said
So,
that that is equivalent to counting the number of points in this spherical shell.
right. So we should have the number of points per unit volume for the this nx, ny, nz.
Yeah, so that is
Kind of
one.
system.
That density is one.
Oh, okay, okay,
Yeah, because you see, it's like one per every unit square or cube.
okay, okay.
Yeah, that you're right. Yeah. So that, but that is one, so it's not a part of the formula. Okay, now we have the number of modes. Now we have to find out the energy for these number of modes in that frequency range. And then comes the classical equipartition theorem. And this tells you that the average energy, so the average energy per mode, per mode or for each mode is basically kT. Okay, and then then to get the energy, then so u nu into d nu, you get n nu d nu into kT. Okay, and if you want this now, so we said spectral energy density, right? So it means that it is per unit volume. So then you divide by the total volume of the cube. Okay, so u nu is energy emitted in the range nu to nu plus d nu per unit volume of the cavity. So that's why we're saying density. So the density doesn't refer to the fact that it is nu to nu plus d nu. It refers to the fact that it is the density per unit volume of the cavity. Okay. We need to
Why
do
is it
this.
not kT by 2? Why is it kT?
This is the average energy per mode uh, for for light. So it has
Ma'am,
both. Yeah.
K is any constant or
No,
specially for like
Boltzmann. No. This is
Boltzmann
Boltzmann.
constant?
Yeah. This is Boltzmann.
There was a two basically we read in last year.
So there is a difference there. So it is half kT for
Is it
every.
because the
Yeah.
is it because the
Continue.
mode is actually vibrational and not translational or rotational? For vibrational modes, we learned that for each mode, the actual value is kT rather than kT by 2.
Yes, because every vibrational motion is associated both with kinetic energy as well as potential energy. So it is the same here. You are right. So it is related to the
There
fact that
only
it's
vibrational is considered.
Yeah, so for light, it is vibration of electric field or magnetic field. And so this is in analogy to vibrational motion of classical particles. Of course, light is not classical in that sense. It's not exactly a vibration. But it can be shown that it is analogous to a vibration. So it has both potential and kinetic energy. In that sense, I mean, you don't talk about potential energy of light or kinetic energy of light, but you can derive it to be analogous, and then you can show that the average energy per mode for light is kT. If you like, I can give you some more details later. We're almost out of time, so I'd like to just finish this section now. Okay, so just two more steps. Okay, so this is so this is n mu by kT, and this is energy per. I hope this is fine. This is then spectral energy density. So this basically is then spectral energy density. Okay. Now I can replace this n nu d nu with the expression that we have obtained. So that will tell me that u nu d nu is equal to 8. So let's see. So 8 pi a cube nu by c square d nu, okay, into kt by a cube. So a cube gets cancelled.
Mom, should that not be a nu square?
U square where?
Nu square, ma'am, the frequencies.
Oh yeah, nu square. Nu square, yes. So 8 pi nu square by c will also be c cube. Nu square kt by c cube d nu. So you see, we have got the classical expression that I showed before with on the plot. So this is it. So it shows that the spectral energy density is proportional to nu square, which leads to the ultraviolet catastrophe. Okay. Also note that the spectral energy density is clearly a function of temperature. So you can, so that's also there. Now sometimes you can write this d nu here or not. So in the notes that I will upload, you will see that the d nu is not there. But it's a matter of how you want to talk about spectral energy density. Okay, but it's fine. And in the notes, they also go on to tell define things like intensity and more, but you can just ignore that part of it. I think just stick to this definition of spectral energy density, that it is the energy in the range nu to nu plus d nu. Okay. So this was the classical derivation for intensity. Next class, we'll do Planck's law. Okay. So I'll stop here now. I'll put up these notes on WeLearn as well. Shouldn't be a
Ma'am,
problem. Yeah?
can you just show the second last page once you put up?
Oh, sorry. Second last page. Just 1 minute. So second last page. Okay, yeah, this one.
Yes, ma'am. Just 1 second. I'll.
Ma'am?
Yeah.
Ma'am, you had previously told that you are using the classical equipartition of energy theorem and taking that half kT for each mode in one of the
Yes.
slides. But here you are taking as kT.
So it's half kT. So we just discussed this. So for light, since it's a vibration, you have both potential and kinetic energy, and there is half kT for each part. So that's why it becomes kT.
Okay, ma'am. So it is for both. We are taking kT for both.
You're taking yeah, kT including both. Yes. So we did not consider separate vibrations. Like we didn't consider the fact that there were vibrations. Right? So that has to be done separately.
Okay, ma'am. Thank you.
Thank you,
Ma'am?
ma'am.
Yeah.
Ma'am, what is meant by mode of light?
Mode of light means so initially we were talking about standing waves. So every possible standing wave is a mode. So let me clarify. Good question. So that then we were talking about standing waves, modes of standing waves, meaning all possible standing waves. Okay. And then when we are talking about the equipartition theorem, then it is the available motions. So classically, for every translation, you have half kT. For every rotation, you have half kT. For every vibration, you have kT. So it's like that. So those are two different contexts of using the word mode. Okay, don't get confused.
Okay. Thank you, madam.
Yeah. Good question. It's important point. Okay.
Ma'am, I
Any
didn't
more
quite.
questions?
Sorry. Yeah, I didn't quite understand like why. Why were people asking like why wouldn't it be half? I didn't exactly understand why that would.
So the classical equipartition theorem tells you that for every degree of freedom or for every possible type of motion in a system, the average energy is half kT. So that is the theorem.
Okay.
And that is what we are using here.
Okay, so they're saying like for potential energy only it should be half kT and kinetic energy only it should be half. But you have taken kinetic and potential combined. Is that it?
Yes.
Okay.
So for light, you can show that. So when you apply the classical equipartition theorem to light, then you get kT basically.
Okay.
If you like, then I can show you more details next class.
Yeah.
Ma'am?
For light specifically. For the classical parts, you have already done this in statistical mechanics, I guess.
Hello, ma'am.
Yeah.
Ma'am, I exactly didn't get this part that light has two possible polarizations.
So light has two possible polarizations, meaning if a light is traveling in the x direction, then the electric field has two possible directions. It can be oscillating in y or it can be oscillating in z. So we did not consider that when we counted the standing waves. So there are two possible standing waves for every direction. So we multiply by 2.
Okay.
Because we want to count the number of possible standing waves, right? So we have to take all the possibilities.
Excuse me, ma'am.
Yeah.
Ma'am, I did not quite understand why we are taking we are making these calculations considering that these are standing waves because the detector is detecting something, which means the waves are traveling, right? So how can a wave be standing and traveling at the same time?
So we're considering that the black body is in thermal equilibrium.
Yes, ma'am.
Yeah. So and we're waiting till it is in equilibrium. And if you have waves which are not standing waves, then they would be absorbed by the body and disturb the equilibrium.
Yes, ma'am. But then these waves will not be coming out of the black body, that box, right? So
So
detector would not get anything, I guess. So standing
no.
wave.
So these are so you assume that you're sort of leaking out the standing waves. You're
Okay.
not really. Uh, so actually, if you really consider it, then just the fact that the waves are coming out of the black body is disturbing the equilibrium of your black body. But you're sort of ignoring that. You're saying it's very little that is coming out.
Oh, okay, ma'am. Okay.
Yeah. So, and anything else? Anyone? No? Okay. So we can stop today then. Thank you
Thank you, ma'am.
for joining the class. Okay.